Appreciate you all joining this morning, and we're going to cover moisture management in buildings, and as it relates to code, but also just the general building science around defining and designing building assemblies so that they are both code compliant and durable over time, and take into account vapor flow through building envelopes. So Alex noted, please ask any questions, put any questions in the chat or raise your hand. I'll stop throughout the content as well to see if there's any questions as we go. But always appreciate a little back and forth while talking into my screen here. So we'll get going. So just first off, to share that this content, a portion of this content is copyrighted by the International Code Council. The International Code Council is the nonprofit entity that publishes the codes. So content that I'm going to be sharing today is coming through them. So fundamentals that we're going to cover in this content today. This is a session that I presented at Better Buildings by Design back at the beginning of April. So if you were there, you saw this there then. If not, getting a chance to catch it now. But material context, what we're building with now and what we need to be aware of in modern building material choices as we define building assemblies and put different components together into a structure. Control layers, that's really kind of the crux of the process in designing building assemblies, is understanding the 4 different control layers and where the critical points of interaction are between those and how to define them in building assemblies. And then the moisture management that kind of dovetails in with all this and relates to all of those assembly, control layer, and material choices as we go throughout the building. So big topic of today's content and anything relating to understanding vapor flow, and I'm going to get that right as I move along here today, through building assemblies is PERMs, and air choice and or the capacity of a material to move vapor through it. And we'll talk about that in a lot of detail here today. So kind of the undercurrent and theme for the content here today. And so stepping back to look at this from the broader context, from the historical context, we are pretty lucky to live where we do here in Vermont, in the Northeast, where our building stock is the oldest in the country. So we have a built environment that's been around for hundreds of years, and these buildings have been, remained intact and durable over that time. And a lot of that has to do at this point with the materials that these buildings are built with. With these buildings, we're all built with materials that were available on hand that could be harvested on site or nearby. Very little adulteration in the materials as they were put together into structures, into building assemblies. And so that is a pretty unique part of our built environment and a consideration for how we use and we modify those buildings to become adaptable and functional as society changes and our needs change for our buildings. So thinking about the context of where we came from to where we are right now and to where we're going, both for the function and use of the building and the material choice of what we work with to assemble buildings. These historic buildings and the character of our environment was built with dimensional lumber that was, like I said, harvested on site or nearby. The wood that was used in these buildings was pretty much the wood as it was grown over time in a diverse forest. And so there's unique characteristics of the lumber and the structure of these buildings that really underpins their durability and the ability for those buildings to kind of adapt over time and to handle the swings that we see in heating and cooling and moisture loading season over season, decade over decade, and century over century. But we are no longer building with that type of material stock. What we are now working with is lumber basically grown as a crop. These are both for practical needs and realistic needs, and also just material and resource management. So We're building with a different type of material, just in the raw form of wood and lumber for what it is. And we're also utilizing that material in a different way than our forefathers did, and how buildings were historically put together before we moved into the modern time and the past century, where forest and wood crops and wood resources have been changed from their original form and put into new dynamics and new structures and new iterations. So that has a significant impact on the capabilities of what we can do structurally with buildings now because of these engineered materials that we're working with. But it also drastically changes the function and capacity and capability of the wood resources that these buildings are built with. So just to take a look to that point of what we're talking about here and that dynamic of how wood actually works is trees suck. That's their job. They were as nature is designed uh, trees and wood and the structure of the material. It is meant and designed to by nature to move water and nutrients from the ground up through the canopy of the tree through capillary movement and pressure difference and suction. We're going to talk about pressure difference and capillary movement as far as how it relates to buildings as well too. But the actual moisture and water and nutrient transport through the structure of the wood is inherent to what wood is as a crop, as a resource, and it also has a significant amount of influence on the durability of how wood is used in structures. Wood in its raw form has the capacity to load and retain and manage by loading and then drying diffusion over time a huge capacity of water when it's in its raw form. So, wood in its raw form is able to do that, but once you start to change and break down that wood and put it into different functional uses, you change the characteristic and the moisture loading potential and drying potential of that material as a result of that use. So beyond just the material choice of moving to engineered materials, breaking wood down from its original structure to be put into another material type or another use, the type of dimensional lumber that we have to work with now is also different because of how it's grown. When we're talking about modern lumber resources that are grown as a crop with no canopy, it's a monoculture, it's a single crop grown quickly, the wood grows quickly, and it's harvested while it's still young. So the growth rings are significantly wider than what a tree that is grown slowly over time under the canopy of other trees would grow. And so the dimensional lumber that we're working with now too is just as susceptible to moisture loading because of the amount of sapwood and the actual carrying capacity of that wood to retain water over time compared to older growth lumber, slow growth lumber that has tighter growth rings, more hardwood rings that are not going to take on as much moisture, and there's more stability in that lumber as a result. So these are all factors that we need to keep in mind in what we're sourcing for use in buildings. Again, a lot of what we're building with now is engineered material where the actual wood resource itself is broken down from its original form and then manufactured into a different type of product and a different type of structural component, which is well and good. And we're able to do a lot of things now that we would not be able to do with just dimensional lumber as far as structure goes and carrying capacity. So from a resource management side, it is the practical evolution of how we use lumber resources effectively in construction. But if we don't understand the dynamics at play in buildings, how to control what we can have control over with those 4 control layers, manage moisture within the buildings, and let any moisture that does get into assemblies find a pathway out, these new modern material choices are susceptible to breakdown and catastrophic failure in short order. Those images I shared at the beginning, like I said, these are buildings that have been with us for centuries, multiple centuries at this point. And one would hope that the buildings that we're building now would be a part of this built environment 100, 200 years from now as well. But unfortunately, a lot of what we're seeing is housing stock that has a lifespan of 40 to 60 years. I think even talking with some builders now, that's kind of what their mindset is that we're talking about a 60-year lifespan for a building, and we really can and should be thinking beyond that. And there's no reason to believe that we can't build buildings that will last for a couple hundred years if we're smart and understanding about the dynamics at play in the structures that we put together. So dive into some of the details relating to that. We'll see if there's any questions yet at this point. Otherwise, I'll start talking about control layers. All right. So in putting any structure together, there are certain aspects of the dynamics of the building that we can influence and have some level of control over. And then there's other aspects to the building and the impact on its durability. They're going to be passive with time. And frankly, once you build and enclose and finish the building envelope and the building assembly, that's where you can define and have some specificity behind the control layers that went into those assemblies. But once it's built, that is a passive component of the building. You are not going to change dynamically anything to do with those assemblies, hopefully over time. So they will passively need to be able to manage the significant swings in temperature, pressure, moisture loading, season over season, and year over year. So that's why getting these control layers and the details right from the outset is critical. So we really have 4 layers that we're dealing with when defining any sort of framed building assembly. And we're talking about walls, roofs, floor systems, etc. So first control layer that we'll speak of is our bulk water control, or the exterior cladding. What the building is going to see to the weather that it will interface with. So whatever the exterior finishes are in the building, with the intent that that exterior cladding is going to shed water and keep it from getting into the structure behind it. Behind that, and somewhere within the assembly, but most typically located at the sheathing, the structural sheathing layer of the building, mainly for in our region, and this is what we'll focus on quite a bit here today, is the air barrier. So the air barrier is the pressure boundary between inside and outside. This is where we are defining where indoor air will be separated from exterior air, and we can create a durable pressure boundary between inside and outside. Because the greater the temperature difference between inside and outside, the greater the pressure difference will be. And pressure will be pushing air from within the building into building assemblies during the heating season. And if the building shell is leaky, if it does not have a good integral air barrier, then we can be pushing a lot of air and consequently a lot of moisture from within the building into these building assemblies, which can lead to problems, obviously, and damage over time. Third, in alignment with the air barrier, is the thermal control layer. This is the insulation. What material we're putting into the building that will slow the transfer of heat energy from inside to outside, outside to inside. And this can be in multiple layers as it relates to the code now. As of last year, we're talking about 2 layers of thermal control, a continuous layer and a cavity layer. So we'll talk about that in more detail. And then finally, the most interior facing layer of the assembly is the vapor control layer. And this is the component of the building envelope that we are defining to slow and retard the flow of moisture vapor from within the building into structural components. So vapor retarder is the best way to define this now. We've talked vapor barriers in the past. There's been some recognition of the concept of trying to stop and think that we can effectively fully stop any moisture vapor from inside the building from getting into building assemblies, and putting in materials into those assemblies with that intention that it's going to be a barrier to entry, to shifting into a mindset of retarder, where we're retarding the flow of moisture vapor into these assemblies. Air tightness at the vapor control layer is critical as well, as it is with the air barrier, and yet giving an understanding and a pathway for drying potential to occur within those assemblies, either inboard or outboard or both, when and if moisture will load into assemblies. Because all the things that we can do to create a durable building structure, we do have to accept that there will be some level of moisture loading into building assemblies season over season. And when that occurs, we need a pathway for that moisture to dissipate and dry out, and for those assemblies to stabilize and remain stable over time. In looking at this as a section view of a wall assembly, just breaking these down into defined locations. So the purple layer there at the exterior, that's going to be our bulk water control layer. Behind this is a continuous insulation, outboard insulation wall assembly. So we have a thermal control layer, thermal insulation, continuous insulation over what would be the WRB integrated with the air barrier. So the pink line being the weather resistant barrier over the sheathing here defined as the air barrier as well, cavity insulation, and then final pink layer on the inside of the vapor control, vapor retarder. And those arrows are giving the indication of where the vapor flow will be into that assembly, and the heat transfer flow will be during the heating season. So the concepts to keep in mind here is that you have those four critical control layers that we can specify and define appropriately to be compatible and to be as durable as possible. But all of those layers have to work together. So you can't get a good thermal control layer unless you've done a good job air sealing, making sure that you have an integrated and an airtight air barrier. So those two things have to occur together and be in alignment. You don't want separation between your thermal control layer and your air barrier layer. The vapor control being integrated in that as well. And then, as I said, the building shell is a passive assembly once complete for the duration of that building's life. But then you do need effective whole house mechanical ventilation to keep the potential of loading in check within the building. And so you need both the passive and the active components of moisture management in the building to remain durable over time. So we're going to start here by talking about pressure dynamics in buildings, and specifically how we deal with defining the air barrier and the purpose and the function of the air barrier. So when we're talking about pressure differential inside, between the building and the outside, there's a lot of different ways that dynamic can occur. So there is temperature difference. Like I said earlier, the bigger the temperature difference between inside and outside, the bigger the pressure difference will be. And this occurs on both ends of the season. So during the heating season, we're got warm air trying to move to cold, and the pressure differential between that. So the dynamic at play during the heating season is that we're getting positive pressure from within the building trying to get out through the building shell to the exterior. During the summer months and the hot days, the flip side of that occurs, where we're getting that pressure differential, but from outside to inside, assuming that the house windows and doors are all closed up. If you got your windows and doors open in the summertime for passive cooling, there's not going to be a pressure differential within the building. But more consequently, what we're talking about here is what occurs during the heating season. Wind has an effect on pressure in the building and pressure drives. So wind pushing on the east side of the building will create positive pressure on that side of the building, and negative pressure on the west side, and suction will occur and can occur across the assemblies when that happens. So that's another dynamic of pressure differential and pressure at play within buildings. And then finally, exhaust and mechanical systems. The code now is at a point where mechanical systems, anything that requires either combustion or would be used for ventilating the building, needs to be balanced, because the tighter you make the building envelope, the less air, makeup air, you are providing to any of that type of equipment through leaks in the building shell. We want the building shell to be as airtight as possible, and then to control the interplay of air movement from within the building to the outside, and then also the need of outdoor air for combustion, for ventilation occurring within the building. So exhaust systems, fans, et cetera, and mechanicals, heating equipment um, is a significant player in existing buildings, and something that we need to be definitely aware of as we modify and retrofit existing buildings. As we start to do things to the building shell to make it tighter than it was originally, that can and will have an impact on the availability of combustion air for boilers, furnaces, wood stoves, fireplaces, et cetera, and the capacity of draft for those appliances as well. So we do need to be paying attention to those impacts when retrofitting existing buildings. So pressure differential is really what we're working against here, and trying to create assemblies that are durable, impermeable to air movement, and are continuous and compatible. Durability is the key here. And that is really, as I said, once we put these assemblies together, they are passive. We hopefully will not be changing them significantly in the decades and years to come after the building is built. So we need to define the air barrier with durable, strong materials that will last over time. And there's a variety of ways you can define an air barrier with a variety of different materials. But again, as I noted, the sheathing layer for 9 out of 10 or more buildings that we build in our climate, in our region, the sheathing layer is that durable, stiff, and layer in the building shell that can create an effective air barrier to the outside. You can do the air barrier in between assemblies. You can use membranes. You can use different things, but really the critical matter here is that they are compatible and durable to stand up over time. And there are a lot of products in the market now that are integrating air tightness into other aspects of the building shell and control layers. So we have fluid applied WRBs that can be put on the exterior of the sheathing layer. That also, because of the nature of how it's applied, creates an airtight assembly of that sheathing layer behind it. Taped sheathing joints of the zip system, or just taping your sheathing joints in general, unifies the assembly. Peel and stick membranes now, peel and stick WRBs that are fully adhered, are highly effective, providing a WRB and air tightness at the same time and in the same layer. So taking advantage of new material choices and options, and understanding the compatibility of those materials in the assembly are things we all need to be aware of at this point. I'm going to shut that door to keep the excitable pooch at bay. So with that being the case, with material options that are available now, one thing, and I'm sure those of you on the call have come across and used, or at least are aware of, are the options for adhesives and tapes on the market now. So pressure sensitive acrylic tapes have been available for quite a while now. The most commonly seen ones would be the pressure sensitive tapes used for the zip system. So that the zip product requires that the field joints of all the sheathing layers be taped to integrate the system together, and you have to roll that tape. That's where the pressure sensitive piece comes into play. So any type of pressure sensitive acrylic tape has a tenacious bond to the substrate and can handle a lot of forces against it, as the substrate that it's applied to can and will move over time. So there's peel strength and shear forces that these tapes can resist that will, again, create a durable, long-lasting assembly with limited risk of failure over time, versus the old school way of trying to make the building shell airtight is going around with a caulking gun and trying to seal up gaps and cracks with caulking. which has some limited application, and durability is a real issue when it comes to caulking. The idea of caulk is to bridge the joint between two materials that will move and create a bond to each of those materials and then stretch with those materials as they move. But inevitably, caulking is typically bonded on all three sides. And then when the material moves, the bond, there's not a bond break there, and the caulking rips and that gap opens up. Air moves through it. And also, not just air moves through it, but if you're using caulking at the exterior, that movement of the caulk and the breaking of the bond in those joints creates the opportunity for trapping and capturing water into these sorts of gaps, which inevitably will break down the materials behind it and keep water in rather than keep water out. So towards the end of the content here today, I'm going to show some alternative options for how to handle and deal with exterior finishes that integrate a drainage plane and also eliminate the need for caulking to accomplish a durable building assembly. So there's a lot of tapes on the market now. This is just a small smattering of what my collection has. So there are multiple types of pressure sensitive acrylic tapes and or other types. Really what you again should be focusing on when using tapes as an air sealing component is that pressure sensitive acrylic type. Do not try to expect that a house wrap tape, clear cellophane house wrap tape is going to stay adhered to the substrate and last over time and create air tightness. You really need to roll it. If it needs pressure, then you know you've got the right kind of tape for the durability. And it's not just that pressure sensitive tape and the adhesive piece of it that's critical, but also the backing and the material that glue or that adhesive is bonded to. So there's definitely a difference in behavior and critically permeability. There's that term again. So vapor permeability of the tapes that you're using to create an air barrier is definitely a consideration to be aware of. These are two right here, pressure sensitive acrylic tapes, both highly durable, both tapes that I've used a lot over the years. Many builders have as well. But between these two tapes, there's a drastic difference in vapor permeability. That tape on the left, the blue tape, is a vapor open pressure sensitive acrylic tape. And that tape on the right is a vapor barrier tape, essentially. So that tape on the left, if you are defining an air barrier that you want to be vapor open, this tape is compatible with the permeability of the substrate that you've used because you want that material to be vapor open and for drying potential to occur through it. Whereas this tape on the right is a vapor barrier tape. So if you are putting that onto a substrate that has similar characteristics, that has either a very low or no vapor permeability, makes sense. But if you are sheathing your walls with CDX because you want a vapor open exterior wall air barrier assembly, you do not want to be using a vapor barrier tape to tape all your field joints of your sheathing. And then beyond those types of paint tapes, there's a lot of different products that are available for window flashings, bituathane embedded tapes. You have to be careful about compatibility with substrates with some of these. They can break down vinyl or other materials that would be commonly in place with windows, window flanges. Backings of the tape from manufacturers as well ease the installation and the intended use of these tapes. So split backings on tapes can be used to seal irregular joints inside corners, other parts of a building that, having that flexibility of folding the tape into a joint that can be very beneficial. And then also gaskets that are the same type of pressure sensitive product, but without a backing to them. These sorts of gaskets can be used at like the termination of a bottom of a wall where you're sheathing an exterior wall, overhanging that sheathing, the height of the band joist of the floor system it's going to be installed on. And rather than trying to tape that sheathing to band joist to foundation joint, this type of gasket can be put along the bottom of the band joist at the exterior before the sheathing is attached and create an airtight barrier there. So a lot of options worth digging into, seeing what's available on the market. Compatibility matters. If the tape isn't sticking, if you need staples to hold the tape in place, then you probably made the wrong choice somewhere along the way. So just because a manufacturer tells you that this foil tape will work with their insulation board, and if it doesn't, don't keep using it. Try to find something else that would work and remain durable over time. Just be reasonable and think through those choices as they come together to make the assembly. Any questions? Okay. Continuity. So it is simple on paper to define where your control layers need to be in a simple building. So as you are defining those control layers, you also should be able to look at section views of the building that you're building, that you're putting together, and see where you can create a continuous line to define those layers around the entire building perimeter. So an example here of a two-story ranch type building, simple six-sided building. It's relatively straightforward to define where you need to have continuity of your control layers, and here are the air barrier. So the air barrier being bottom, the walls, and then continuing at the top of the building. And in this example here, one of the critical things to be mindful of is that if you're using your sheathing layer as your air barrier, then your sheathing layer being the outboard most layer before your siding of the building being your air barrier, you need to understand how you're going to carry that continuity to the inside of the building when you have an open flat attic assembly above it. In this scenario, you are defining your air barrier at the ceiling. And so you can use sheathing. Here's an example of a builder who's used the zip sheathing to create an airtight air barrier assembly at the ceiling plane to the attic above. And that's another example of how that can be done. You can use sheathing at this layer. You can use a vapor control membrane that is strapped, and then your interior drywall or finishes will go over it. But it doesn't have to be complicated, and it does not have to be a sheathed ceiling plane or even a membrane specifically, depending on the assemblies you're putting together behind that. But it can be a simple material and process of just detailing whatever that ceiling plane will be to make it airtight. So if you're using drywall as your vapor and air barrier control layer at the top of the building for an open attic above, then using spray foam or other products like that to air seal all of your penetrations to that open attic space before blowing in or adding insulation can be just as effective when done right as defining that ceiling plane with a layer of sheathing or another specific airtight vapor control membrane at the top of the building. So we don't need to go down the road of needing to change process, change material choice, add new cost or new steps in the construction process. We just need to understand where the continuity can occur and make sure whatever we're defining is durable for the longevity of the assemblies we're putting together. Quick coffee break. So defining those 4 different control layers, a critical piece of the puzzle that we all need to be aware of at this point and looking at when defining what choices we're going to have and what we're going to use in each of those 4 layers is that perm rating. What is the vapor permeability of any of the given materials that are put together into an assembly? So what's the vapor permeability of the WRB, of the sheathing layer or substrate behind that, of the thermal control or insulation layer in the cavity and or continuous behind that as well, and then the vapor permeability and or vapor retarding capacity of the vapor control layer that is most inboard to those assemblies. So a perm rating is basically the material's ability to transfer moisture in its vapor form through that material. So 1 perm equals 1 grain of water vapor per hour, per square foot, per inch of mercury, or pressure. So we're not talking about liquid form here, we're talking about vapor form. And why this matters is because if you have moisture vapor moving through material from the inside of the building and loading into an assembly where it can accumulate over time, if that moisture vapor in the assembly starts to accumulate and find a cool enough surface, it can transform from its vapor state to its liquid state, or in the winter, it's frost often, and accumulate into the materials within that assembly. So this is why understanding how pressure and air movement affects vapor transport, and then understanding the capacity and capability of the materials in those assemblies to handle moisture if and when it does see it. So I'm going to, well, so for an air barrier, it matters. Why the vapor permeability matters, because that is the most typically the outboard layer, if not continuous insulation that's outboard of the sheathing, that any moisture vapor driven into those assemblies will see. And so you have significantly different dynamics at play if you have a very low vapor permeable exterior sheathing, or a vapor barrier, essentially exterior sheathing layer and or continuous insulation layer, versus a vapor permeable sheathing and or continuous insulation barrier. Those are two sides of the equation there, and oftentimes we land somewhere in between. So again, understanding the capacity of the assembly to dry out over time, because it will inevitably load some moisture, we need to be considerate of that when defining what our air barrier layer is going to be, the characteristics thereof. So just kind of simply put, for our structural sheathing layer, we kind of have a limited number of options. You can sheathe a building with dimensional lumber. I'm seeing more of that now than I've seen in the past. So builders who are looking to build very completely vapor open assemblies, entire performing building assemblies, have been using diagonally oriented 1x dimensional sheathing as a structural sheathing layer, which again, that wood being in its raw form is very vapor open. That any moisture vapor that would see from inside the building is going to, if it loads into that wood, that 1x material, it will dissipate easily over time, because that wood has not been changed from its original form. The next step down from that, as far as vapor permeability goes, but still considered a very vapor open sheathing option, is plywood, CDX. So veneered layers of wood that are peeled off of a log and then glued together to create a structural board is, in this scenario, we're talking about wood that is less adulterated from its original form. So because it's more of the carrying capacity of the wood is retained, more of the structure of the wood is retained, we have a higher perm rating material, so more highly vapor open as far as a structural sheathing product goes. So plywood CDX typically has a perm rating of about 10. Then going to oriented strand board, OSB is taking trees, again, crop lumber, and breaking it down into flakes, and then orienting those flakes and layers, and then gluing and bonding those layers together under pressure. So because the wood is broken down substantially from its original form, there's very little vapor permeability through the wood and very little capacity for diffusion once that material sees moisture or water. So oftentimes OSB sheathing, if it gets wet, it will stay wet. It has a hard time drying out. The species of wood that's used in the OSB has an impact on what its perm rating might be, as well does the ratio of glue and binders, et cetera, in the material itself. But basically what we're talking about here is a very low perm rated sheathing material, anywhere between 1 and 2 perms, and sometimes less than that. Air tightness is also differential depending on the manufacturer and the wood types and composition of OSB as well too. Under pressure, it's been tested to be both airtight and somewhat leaky. So there are different characteristics here in consideration when choosing OSB versus CDX. Advantech or zip sheathing is a even more resilient and durable version of OSB, a higher density of resins and waxes into the material. That creates a highly durable sheathing product, especially the Advantech product. You can effectively understand with that product that if it sees any moisture from the inside of the building or from the outside, it will not absorb into the material because of that high density of resins and wax in the product itself. But that also means that you effectively hit a vapor barrier in that material at the exterior of the building. The zip sheathing itself, the coating that is put on the zip sheathing as the vapor permeable WRB has a perm rating of about 16. The OSB that it's bonded to is not the Advantech product, so it does have some moisture, some permeability, but again, it's a very low vapor permeability, so typically under 1 for the substrate here. So using the zip sheathing and or the zip R product with the integrated insulation, continuous insulation layer, you have to be considerate of the fact that that material is, you're not going to get very good, if any, drying potential whatsoever to the exterior in that assembly. You're going to need to give a pathway for any moisture loading within those assemblies to be able to dry to the inside of the building. So why this matters, again, you know, in these assemblies, in these photos here, we're looking at wall assemblies where pressure differential was not accounted for, and a good airtight air barrier was not built into these assemblies. So you have a lot of vapor transport due to pressure differential throughout the heating season. You also have limited drying potential within those assemblies and high capacity for moisture loading and saturation within the materials in these assemblies. And this is what you'll see and what you can see as those dynamics accumulate season over season and over time, and the breakdown of these assemblies that can occur when you're not taking into account the understanding of how pressure and vapor flow and vapor management of material choice comes into play in building assemblies. Any questions? No. Okay. So shifting to the outside again here, and weather resistive barriers and the capacity for both drying potential from inside and also the resistance of wetting from the exterior, which is what the function of a WRB is. You know, a lot of what we know the energy code here in Vermont, the RBs and the CBs codes, because the state of Vermont adopted those as being required for their applicable construction type here in Vermont and the code of effect, essentially. That being said, the International Energy Conservation Code, from which the RBs is modified and updated from, sits within the broader International Residential Code. So the IRC is the overall substantive building code that applies to single family and to duplex type homes, which is the building typology that RVs applies to as well as multifamily up to 3 stories in height. So in context, there are definitely the state of Vermont has not adopted the International Residential Code, but there is context there to be aware of and sections within RBs that reference sections of the IRC. Specifically to what we're talking about here right now are the sections of the IRC that define the criteria for exterior weather-resistant barriers, what are considered approved WRBs, and testing standards for manufacturers to meet if they are defining or designing WRBs for use that are code compliant. So It is something to be aware of and to dig into a little bit deeper too, not just be aware of the RB's requirements, but look into the references that exist in the IRC that interact with the requirements of RBs. As I said, specifically here to WRB. So WRB is required based on the IRC. 15-pound felt is considered a code compliant WRB, and then ASTM standards for testing of other materials or other products that may be used as a WRB. So there's a lot of them on the market. We don't just have Tyvek and Typar to choose from anymore. So we have a variety of different WRBs that are available now. A lot of them now as well too are integrating other aspects of durable wall assemblies to include drainage planes, and then also some sort of drainage mat into the WRB that's integrated into it, as well as the self-adhered option as well too. So that self-adhered WRB also then creates an airtight air barrier. So there's benefits to these new products on the market that can reduce the number of trips around the building when putting together your building assemblies. But there's also significantly different characteristics of WRBs, how they are designed and manufactured to manage vapor transport, and some considerations you might want to look into when choosing a WRB, not just what product is cheap or available from the yard. One of the more significant differences in how some WRBs are manufactured are how vapor transmission from the inside is intended to occur through the product. So the idea of a WRB is that it will prevent any wind-driven or exterior-driven water from the environment that would get behind the bulk water control or siding layer and get to substrate behind it. The WRB is there to protect the vulnerable wood product and sheathing layers behind the siding. So it is intended to shed that bulk water from the exterior, yet still at the same time allow for any vapor drive from within the building to move through that material and then diffuse to the outside. That vapor that would be diffused through the material or drying through that material does need some space and place to go. That's why we are seeing more integrated drainage planes now. I'll talk about that a little bit further on. But significantly, as a difference between different manufacturers, spun polypropylene vapor WRBs, so like the Tyvek and the Typar, some of the original WRBs that were on the market versus felt, are the way that vapor transmission was designed to occur through those materials was through very microscopic small holes in the material. The way that the material is a spun polypropylene, so spun or stretched or put under heat, that would create these little micro tears and holes in the material, which is the intended mechanism for vapor diffusion through the material. So those types of products are dependent on a level of pressure differential between inside and outside to allow for that vapor transport to occur. Again, we're getting very airtight building assemblies now and very good air barriers. So there's little vapor pressure or little pressure between inside and outside now. So it retards the capacity of vapor transport through that type of product versus other products that are available on the market now from manufacturers where it's an actual film, engineered film that does not require or rely on pressure differential for diffusion to occur through it. And then that film is protected on both sides by a fleece backing. So it's kind of like the Gore-Tex concept. So it's the idea of a Gore-Tex type layer where it's actually an engineered material designed for vapor transmission to occur through it without relying on tiny little holes in the product for that to occur. So just as a quick example here, Tyvek, very high perm rating because of that spun polypropylene type of manufacturing process. It is not airtight as a result of that, so you can't use a product like Tyvek and define it as an air barrier to an assembly because it will not be inherent to the way that the product is manufactured. Solitex Mento from Proclima. This is a European product and one of the European products that is using TEE film, so thermoplastic elastomer ester. It's a film, again, engineered specifically to allow for molecular diffusion across it, so from one side to the other. Does not rely on a pressure differential for that to occur. Still has a very high perm rating, protected on both sides by a fleece backing. Different versions of these products are available for different uses, for roofs versus walls, some self-adhesive products available here now too. So that is different material type than the spun polypropylene. Hydrogap from Benjamin Obadike is a similar, proprietary sort of film membrane that is allows for vapor diffusion to occur across it, protected on either side by a fleece backing. The Hydrogap integrates these little 1 millimeter thick rubberized nubs that create a drainage pathway before the exterior siding is put on. So basically, what the Hydrogap and or other integrated drainage plane mat type WRBs that are on the market allow for is a capillary break between your exterior finishes and the WRB behind it. That capillary break is critical because if you are getting vapor drive through these assemblies with the intent of drying potential to occur to the outside, what you don't want to have is that vapor being diffused through this WRB just immediately come into contact with the backside of shiplap siding or bevel siding, whatever type of exterior finish is on the building. That capillary break provided by the Hydrogap and other drainage plane assemblies allows for that vapor that would be moving through that material to just have a disconnect and a space for drying and diffusion to occur to the outdoor environment. So integrated drainage planes, if not a physical drainage plane, are also a critical component of these durable assemblies and for durability of exterior finishes. If you're integrating some sort of drainage plane into an exterior finishing assembly, you can trust that those exterior finishes, that siding, that trim, if you create that capillary break and that separation, is going to need a lot less maintenance and a lot less painting and finishes over time than what we've gotten used to accept with siding applied directly to the substrate behind it, where a lot of moisture loading from within the building and the exterior too can impact the durability of the siding and the exterior finishes. All right, any questions? No. So continuous insulation wall assemblies. So the 2024 Vermont RBs, which went into effect last July 1st, now requires some sort of continuous insulation wall assemblies. So the prescriptive requirements in the code have now gone from an R value for cavity as a minimum that needs to be met to a U factor of the total assembly. So U factor is taking into account the characteristics of each of the components and each of the layers into an assembly. And so a U factor is the minimum requirement that needs to be met for any framed assembly. So ceilings, enclosed slope ceilings, above grade walls, framed floors, etc., are all being evaluated for code compliance based on the assembly itself, not just the cavity. So this is what we're looking at when defining how to come up with the U factor for an assembly, is rather than just seeing R values for cavity, we're now looking at cavity plus continuous. Each of these layers is considered into that calculation of the U factor. So taking in the characteristics of each layer and each component and percentage of the building of those components, that is framing versus cavity, etc., generates a U factor for the assembly. So for above grade walls, we are needing to come in at a U factor of under 0.044. So the higher the U factor, the less performing the assembly is. The lower the U factor, the better. Let's see if there's any questions. There's a 1 millimeter drainage plane gap large enough for the size of a water molecule. Yeah, that capillary break is really what is necessary. The bigger the gap, the more drying potential you would have. For more in that scenario, exterior driven moist water that would get into the assembly behind it. So if you have an open rain screen or some sort of exterior finish that siding that has gaps between the cladding, for an aesthetic or finish standpoint, you'd want a larger gap behind that material and the wall behind it to allow for bulk water to escape. But if we're just talking about for drying for convection purposes, then yes, just a small capillary break is enough to create that capacity to occur. So reasons behind building continuous insulation walls. The key thing is it eliminates thermal bridging. You're not getting conductivity through the framing components of an assembly anymore. And that's consequential when you have typically about a 20% framing factor for most buildings, built 16 on center. That is going to be about your percentage of framing. So it eliminates the heat transfer through those structural components, which has a pretty big impact on your heating and cooling loads for the building, more consistent comfort throughout the building. And done right, it can eliminate the risk of condensation to occur within wall assemblies. But if it's done wrong, or with not everything considered into equation in those assemblies, you can increase the risk of condensation and damage occurring in building assemblies. So this is the critical piece to be aware of when defining how to get to these assemblies and get them to be code compliant, but then also durable. There's definitely a difference in what the code requires for that EU factor of 0.044 for above grade walls, and how to get there in a durable and safe way for the long term of that assembly. So some options for building continuous insulation wall assemblies. It doesn't always just have to be a layer of literal continuous insulation as a board sheathing, either inboard or outboard of your framed wall, of the framing cavity. Double wall construction has been around for a long time. You build two wall structures and fill the cavity with a dense packed insulation. And you can create whatever level of effective R value by the depth of the assembly. So the spacing of the framing, the gap between, and the overall depth of the cavity are your options for controlling what your overall effective R value would be for those types of assemblies. When you're going to use a double stud wall as your method for accomplishing a continuous insulation assembly, there are definitely details that need to be accounted for, and working with a qualified and experienced installer of the insulation in those assemblies has a huge impact on the overall durability of these types of structures. So one of the benefits of using dense packed cellulose in a double stud wall assembly is that these types of assemblies can manage and load moisture, and quite a bit of it, season over season, and still remain dry and durable over time. So cellulose has a high capacity for loading moisture, but then diffusing that moisture throughout the material, and then a high capacity for drying season over season. So if you do have moisture loading into these assemblies during the heating season, as long as you have a potential for drying, highly effective potential for drying to the exterior and or the interior, any moisture that's loaded in that cellulose during that heating season can effectively dry out and stabilize, and the cycle continue year over year without things breaking down. In order for this to work effectively, you have to have an effective dense packed assembly where you do not have gaps or voids or settling occurring in those deeper cavities throughout time. So it does take calibrated equipment and an experienced installer and appropriate definition of different blocks of cavities in order to get this right. So you can't just blow cellulose into a whole wall system and effectively get it dense packed. You need to break those assemblies down into sections with netting and effectively pack each of those sections one at a time. The methods for doing this are properly calibrated equipment, using bag counts, weighing out material. So the details matter, as with any other aspect of construction, but getting to the right amount of density comes down to, again, knowing how to use the unique characteristics of the material and how it's installed to get to that density and durability over time. So, isolating cavities here, so you're not just filling the full rafter bay from top to bottom, using a netting that allows for the air that's being blown in under pressure with the cellulose to escape easily. You can use a interior vapor control membrane to dense pack behind it, but in doing that, you are limiting the amount of air that can escape through that material under pressure when you're doing your dense pack. So it can be challenging to get to proper density when using some of those materials. So often, when dense packing before an interior vapor control layer is put up, just blowing behind this InsulWeb or netting is the effective way to go about getting your proper density in these assemblies. So alternative to double stud wall assemblies, nail-based panels. So the Zip-R product being the most common in our area, I've been seeing a lot of this being used to get to continuous insulated wall assemblies. There are different thicknesses of different R value available from the manufacturer. These are rated as structural sheathing components as well. So in order to get to that structural rating, which is the intent of integrating, the insulation, the WRB, and the sheathing all in one layer, is to eliminate multiple trips around the building to get each of those 3 layers installed. But in order to make it a structural assembly, you do have to follow the nailing patterns from the manufacturer and carefully tape and seal all of your joints. So there's different thicknesses here of different R values, some challenges and opportunities depending on which thickness is used. But again, I'm seeing a lot of this being used for meeting code compliant continuous insulation assemblies. SIPS panels, so structural insulated panels, are another option that I think is something we will be perhaps seeing more of now with the code requiring continuous insulation assemblies. An actual structural insulated panel rather than just a stress skin type panel. So oftentimes we see SIPS panels used to enclose a timber frame, where the timber frame is the actual structural component of the building, and these SIPS panels are not actually structural in those scenarios. It's really just the creating the exterior building shell, insulated building shell. But when used as a structural panel and engineered, you can have the entire assembly, wall and roof assemblies of a building built in a matter of days, and a highly effective continuous insulation structure built. But it does take careful detailing, a good manufacturer, and a good system for dealing with the joints and splines of putting the panels together to make sure that they're airtight and not vulnerable to moisture loading at the seams. And then the final option, and there are other ways of doing continuous insulation. Obviously, these are not all of them, but I'm just kind of sharing the most common approaches that we're seeing in the industry. But exterior continuous insulation, where you're framing your structural wall assembly, sheathing that wall assembly, and then putting outboard insulation outboard of the sheathing layer. And this can be done with a variety of different materials, a variety of different thicknesses. Again, the code requires a 0.044 wall assembly to be code compliant. That can be done with R20 in the cavity and R5 of continuous insulation to get to a 0.044. That being said, from a building science standpoint, from again, going back to the earlier slides of mitigating or eliminating the risk of condensation occurring in the assembly at that vulnerable sheathing layer, the wood sheathing layer, because that's what can be damaged and broken down if it gets wet and stays wet, is the ratio of 50% of what the cavity insulation will be in the continuous layer. So if you can do that ratio of exterior rigid insulation to what is in the cavity, by doing that, you can effectively keep your sheathing layer warm enough to be above the dew point throughout the heating season, so that you would not get any condensation occurring within the wall assembly by moisture vapor that would be driven into it from the interior. And consequential to that as well too is what are your material options and choices when using both cavity insulation and continuous insulation. It really doesn't matter, honestly, what type of insulation you are using. Any insulation type can be effective as long as you're understanding the characteristics of the material, what its capacities are, and what its constraints are, and then how it interacts with the materials on either side of it and surrounding it in those assemblies. So there's not one that's worse or better than the other, but compatibility and understanding how the different layers affect the durability of the assembly are what counts and what matters here. Because what you don't want to see is, insulation in the wall and then mold and mildew from condensation occurring behind it. So when it comes to options for continuous insulation of rigid board insulation, a lot of options for that on the market as well too. Different R values per inch, different levels of vapor permeability, and different aspects of the facings that are applied to these materials as well. So in this example here, we've got a mineral wool rigid board material that is very vapor open, completely vapor open essentially. Next to that, we have extruded polystyrene, a effective R value of 5 per inch. That mineral wool is effective R value of about 4 per inch. The XPS has a perm rating of about 1 or a little bit under, so mostly vapor closed, but some limited potential for drying through it depending on the thickness, again, of the material as well too. The thicker the material, the less vapor permeability it has. And then we have phenolic foam board, an R value of 8 per inch, but also a very low permeability material, and that is also impacted by the facings on the material itself. And then finally, polyiso foam board, effective R value of about R6.5 per inch, and also effectively a vapor closed material. So depending on which of these types of material you would use as an exterior board insulation is going to affect the characteristics of that assembly's drying potential, whether it can dry freely to the outside, and that would impact the choice of the WRB in place, or if because of that rigid exterior insulation choice and or the facing or backing on it will limit or retard or stop the potential of vapor flow through that material to the exterior, you're going to need to define other components in the assembly that will allow drying to the interior. So essentially, unless you're using a wood fiber or mineral wool or a fiberglass board type product outboard of your sheathing as your continuous insulation layer, any other foam board type will really rely on that wall drying to the interior. So you need a good airtight vapor retarder membrane on the inboard side of these assemblies, but that will also allow for drying potential and vapor diffusion through it to the interior during the warmer months of the year. If you're using wood fiber, mineral wool, fiberglass board on the outside of your wall assemblies as your rigid insulation layer, and if you sheathe that wall with CDX or 1x material and you have an effective WRB integrated with that, that wall assembly will have good drying potential to the exterior and or the interior as well too, depending on what your choice is for vapor control. So as we start to get into vapor control here integrated into these assemblies, again, this is another spot in the ARBIES code that references the International Residential Code. So when you're looking at what the code requires or calls for when doing continuous insulation assemblies, this table R702.7 in the IRC code defines where class 2 vapor retarders can be used. And these are continuous insulation assemblies. So for a typical 2x6 wall, anything with a continuous insulation layer integrated with that of an R5 or greater, a class 2 vapor retarder can be used. And then moving to a class 3 vapor retarder, this is for our climate zone. requiring that ratio of what I was just defining a moment ago of, for a 2x6 wall assembly, a minimum R value of 11.25 that would be installed outboard of the sheathing layer would allow for a class 3 vapor retarder to be used in these assemblies. So the idea of a vapor retarder or vapor control layer is to retard and mitigate and limit as much as possible the flow of moisture vapor through diffusion and air leakage into the assemblies behind it. The diffusion is the piece of what the vapor retarder is intended to mitigate against. But again, if you're not installing that vapor control layer with consideration of the air that can get behind it and air leakage around the plane of the vapor retarder, then you are kind of eliminating the potential of that material to do what it was designed to do. Because if you have a lot of air leaking behind the material or around the material, then it's not going to stop the bulk amount of moisture getting into the assemblies behind it. So creating air tightness at the vapor control layer is critical as well. And your options for vapor control land in the buckets of either class 1, class 2, or class 3 vapor retarders. Class 1 vapor retarder is basically something, a vapor barrier that is 6 mil poly. It would be high density closed cell spray foam. It would be aluminum facings on rigid insulation board. Those are all vapor barrier type materials. But what we're typically working with here in the assemblies that we're building at this point, especially with continuous insulation, and as the IRC notes, we're looking at class 2 or class 3 vapor retarders. So a class 2 vapor retarder is anything that is has a perm rating of 0.1 up to 1 perm. And then a class 3 vapor retarder is anything from 1 perm to 10 perms. Any questions? So as noted with the other parts of these assemblies here, we are building and defining into these assemblies components that will be passive over time, right? So the materials need to behave and work well together and create the intended function of mitigation of loading of moisture and then drying if when and where it needs to occur. But we also need to manage the generation of moisture within the building to not put additional or extended load onto these assemblies. So we need to be able to keep the indoor environment in check. So for both relative humidity and the generation of moisture that's occurring within the building to be managed, but also to just keep overall general indoor air quality in check, eliminating chemical contaminants, VOCs, pollen, allergens, etc. So higher humidity can increase those problems within the building, as well as create the conditions and the potential for mold and mildew to grow and occur within building assemblies and in other areas. Part of what we are needing to be aware of when defining vapor control in the building is what I was just speaking to, is you have a vapor control membrane that will be effective against diffusion through the material. But if you're not taking account of the pathways for air to get behind that, you are opening up the potential for the bulk of moisture being moved into assemblies due to air movement. So the air barrier, if that is in good shape and very effective, then you're not going to have a lot of pressure differential between inside and outside. So you're getting a bulk of your protection through that. But otherwise, you do need to be paying attention to the details of that vapor control. So just as an example, this is a great old school reference from Building Science Corporation. Over a full heating season in a cold climate, over a 4x8 sheet of drywall, where the interior temperature is 70 degrees and about relative humidity of 40%, which is about where you'd want to see it. Between 30 and 40% is about where we want to see relative humidity stable within buildings in cold climates. Just by diffusion through that material, about a third quart of water would be transported through that material into the assembly behind it. But if a 1-inch hole was put through that sheet of drywall, and there was a pressure differential between that wall inside and outside, up to 30 quarts of water can be moved into that assembly through that same 32 square feet of surface area when you start to integrate or introduce the potential for air movement to transport moisture vapor into building assemblies. So critical components here is pretty straightforward. We try to control humidity as much as possible in the first place. That's the primary mechanism at play here. And then if and when indoor air is going to come in contact with surfaces, try to keep those surfaces above the dew point. Keep it warm or don't let it get there in the first place. So, when you're looking at wall assembly, this is the dynamic at play where you've got warm air with, in this scenario, 50% relative humidity at 70 degrees, and the outdoor air temperature is 0 degrees. You have a diminishing curve of temperature in that wall assembly, and you will reach a point where the backside of that exterior sheathing will be cold enough that condensation will occur. And the worst thing that could happen there is wet funk, and we don't want wet funk in our wall assemblies. And this picture right here is a cutout of OSB with fiberglass from a 2x6 wall, and that is not spray foam that's bonding the fiberglass to that OSB sheathing. That is frost that is bonding that fiberglass to the OSB. So this is just a physical example of the dynamic at play that we're trying to prevent against. And again, the damage is real. This damage can occur in short order. The houses here in these examples with the siding, those are not, 100-year-old homes. Those are 20-year-old, 30-year-old homes that this type of damage is occurring on, perhaps even less. So 3 critical rules: keep water out. If water gets in, give it a pathway to get out. And if the material might see that moisture or that water, keep it above the dew point. So vapor variable membranes are products that have been around now for at least the past decade in our market. In the Northeast, we started to see products from Europe come over about 2014, 2013 or so. These are, and then there's also manufacturers in North America that are making these products as well, and more players coming into the market right now. As well, Benjamin Obdike has just come out with a vapor variable membrane as well. So these are called a variety of different things: vapor variable membranes, intelligent vapor retarders. When these products see relatively low humidity during the heating season, and so we're talking again relative humidity between 30 and 40%, the material itself is tight. It performs as a vapor barrier, vapor retarder at that point. It retards the transport of moisture vapor from the warm interior side into the assembly behind it. But then consequently, during the warmer months of the year, when we're seeing, summer-like conditions and relative humidity 60, 70, 80%, during those conditions, the material opens up, and any moisture that would have accumulated in the assembly behind it can now diffuse to the inside of the building. Because the dynamics at play during the summer months as well too is that the pressure and temperature differential is driving moisture into the building rather than going from the interior of the building to the exterior. So when you're looking at these products and considering the options available, you're looking at the range of permeability between winter versus summer performance. So the Intello Plus product from ProClima has the lowest perm rating during those wintertime low humidity conditions, so 0.17. So considered a class 2 vapor retarder, very close to a class 1, but then opens up substantially during the summer months. Opens up to a 13 perm rating. And then you'll see a range of other performance from other products that are available on the market. So as I see these, it's kind of an insurance policy to the durability of these assemblies behind it. Trying to install the material again to make it airtight. So when you're defining the assembly and putting them together, gluing the material at the top plate of the wall, at the bottom plate of the wall, at the perimeter of window and door rough openings. That will prevent the bulk of air from getting behind this material and the integral performance of the material as a vapor control layer to the entire assembly. Taping any holes that would have been punched through it for dense packing of cellulose or other needs. But if you can get those details right, then you are going to be preventing 80, 90% of the potential for moisture loading into the assembly behind the material. Where you have transitions that are all framing, blocks of windows installed, where you just have stacks of supporting framing components, using a compatible airtight vapor open tape can be used in place of using the vapor control membrane, but making sure that you're integrating this all to make it airtight, and then your interior finishes going up over top of those components. You don't need to rely on the drywall being airtight at that point, because you've already detailed your vapor control layer with those details in mind. For some thicker wall assemblies, if you're doing double studs, then strapping the interior of the wall assembly both helps with interior finishes because of the potential of bulging out of the dense pack layer, but also creates a potential for a service cavity where wiring and interior mechanicals can be run without penetrating into the insulation assembly behind it. But you can do this without you can get high performing assemblies without taking these extra steps as well. Considering how these control layers are going to be woven into construction is critical as well. It's good to have these products on site during framing to ease the integration of the vapor control layer into the assemblies. It's much easier to detail this by putting that layer of vapor control up before the interior top plates are installed, the blocking is in place. So integrating these into the full process of construction as well. Vapor control can be a combination of materials here as well too. So you have a wall assembly with dense packed cellulose behind it and a vapor control membrane over it glued at the top plate. That transitions into closed cell spray foam into a very low slope roof above. And the closed cell foam in this scenario is the vapor control layer and a vapor barrier in that scenario. Window and door rough openings, making sure that those are both insulated and airtight and are preventing moisture vapor from getting into those gaps and getting to the cold window flange behind it. Also needs to be integrated into the assemblies and thought through. You can use gaskets, you can use tapes, you can use foam, you can use foam and tapes. So there's a variety of ways to deal with those penetrations as well. Then finally, looking at ways to do drainable exterior finishes. So when we're doing these thicker layers of continuous insulation outboard of our wall sheathing, it changes significantly the dynamics of how our windows are integrated into the assemblies, how the corners need to be done, how doors are installed. And if you're using strapping as a way to create a drainage plane and also a structural connection for your continuous insulation, it can open up opportunities to create highly effective and very easily drainable and dryable exterior finishes. So integrating flashing back to the WRB in continuous insulation assemblies is critical. And then how your drainage plane is going to interact with that as well. You need to be looking at these details and figuring these out ahead of time. So in this scenario here, we've got 3 inches of continuous insulation with a built-out window buck that planes out with the face of the continuous insulation, but all of the flashing details from the face of that window at the plane of what the wall will see from the exterior, everything is flashed back to the WRB, which is behind that continuous insulation layer. So the taped foam board in this scenario is really just to protect the tape or protect the foam board itself. The critical details here are the taping and the flashing to the WRB behind the insulation material. And so just here's an example of that in process. WRB, window bucks, taped back and flashed back to the WRB, the layer of continuous insulation installed, planing out with the window buck, strapping, and then exterior finish. Strapping does not need to be oriented vertically to create the effective break and capillary break and drying potential to the surfaces behind it. So, as the question noted earlier from Keith, you just need separation from those exterior finishes to the materials behind it. So you don't need to worry about directing where water can move. Again, just that small capillary break of the material to the substrate is enough that any vapor drive occurring through that material just has some circulation and is not in direct contact with the material that could be damaged if it gets wet and stays wet over time. And as I noted, the manufacturers of exterior products have all seen what the codes require now, seeing the direction of where we're going, of what creates and makes durable assemblies, but also what the code requires. So a lot more products now that are integrating these drainage assemblies into WRBs and exterior finishes. So really, it's something that it's hard not to integrate into assemblies at this point. And then finally, making it all look good in the end, again, the caulking piece, this is something that we do not have to carry old ways just because this is how it's always been done. Anybody who does that has caulked exterior finishes and trim work, inevitably you see this type of damage. Again, because the materials will move, and if and when they do, and those gaps open up, what you intended to do is to stop water from getting in, you're trapping water that has gotten in at that point. So the best of intentions can and often does still lead to failure in these sorts of approaches. So looking at new ways of putting your exterior finishes up that doesn't rely on trying to keep the water out necessarily, but just effectively understands that if water does get behind them or does get in from the exterior, it can just freely and easily drain out, dissipate, or diffuse to dry. So there's different aesthetics that can come into play when doing open rain screen sort of exterior finishes, and that aesthetic can build to what the look of the building will be, but also it doesn't have to be some modern aesthetic or use some specific material choice. You can also do more traditional quote unquote exterior finishes as well. But just creating, again, this pathway for water to not collect and be trapped in any specific area, but just simply to be able to dry out. And so when we look at some more traditional finishes, clapboard siding with traditional window trim, the ability of being able to put that siding behind the window casings and corner boards, no caulk anywhere at any of these assemblies. Any wind-driven rain that gets behind that siding or behind that window casing is going to drain out because of that 1x3 airspace, strapping space behind it. This also helps ease the installation of your siding too. You don't have to spend the time of carefully cutting to length each of these pieces of siding because you have the end cuts being protected and hidden by corner boards and by your window casings. And you also don't have to go around the building caulking all of these joints as well too. So just some different ways of considering how to put together your exterior finishes, benefiting from what we know are durable components of the control layers that are also make for code compliant assemblies. So that is what I have for you here today. If you have questions, you want to dig into things a little bit more detail, we always have the Energy Code Assistance Center number available to call. You can get your questions answered there, or you can be put in touch with myself or another colleague that can get into it in more detail with you. We are doing code support site visits at this point as well too. So if you are interested in talking further about a specific project you're working on, and you'd like to dig into the details, feel free to contact me here by email or give me a call. I'd be happy to talk to you about your project and help set up a site visit or a meeting to discuss in more detail. So thank you for being with us here this morning. I will stick around for any questions.